Hey guys, welcome to the seemingly last problem for application of differential equations. We've solved 4 problems in this series so far, and this is the 5th problem. So if you have not watched for the solutions of the first 4 in different areas of applying differential equations, first order differential equations, you can check the playlist and see the applications and try to learn them, and make sure you like, make sure you subscribe, hit the notification button. So let's move on to the last problem, which is still under radioactivity or the growth/decay problem. So clearly this is actually a radioactive decay problem. So let's dive into the question and see what we're dealing with here. So we said the rate of decay of a radioactive substance is proportional to the amount A remaining at any instant. If A equal A naught at T equals 0, prove that if the time taken for the amount of the substance to become half A naught is T, then A is equal to A naught exponential minus T ln 2 over T. Then prove also that the time taken for the amount remaining to be reduced to 1 over 20 A naught is 4.32 T. Okay, wow, this one looks kind of intimidating, but let's see how intimidating it can get. Solution. Alright, so I used a white chalk for you guys today. I hope you're going to like the white chalk. A lot of inspiration comes with it. Now of course we can see that A of T is the amount of substance remaining, or rather I should use the word present, at any given time T. So according to the question, it said the rate of decay is actually proportional to what the amount remaining at any instance. So the rate of decay, dA dt, is actually proportional to the amount remaining, and this is going to be in negative A. Remember, when you're dealing with decay problems, you should always use negative A in this case to represent the amount. So if you introduce your constant of proportionality, you get minus what? Ka, as your rate of decay equal to minus Ka. So this is the beginning of the model of our system, like this. So let's go, this is equation 1. Now if you solve for this particular equation using separable variables, this implies 1 over A dA is equal to minus K dt. Is that okay? So when you solve using variable separable, then you integrate both sides with respect to, of course, the prevailing variable for each side of the equality. On the left hand side we have A, and on the right hand side we have T. So integrating with respect to A on the left hand side, I'm going to get natural logarithm of A, and integrating with respect to T, I'm going to get negative KT, where K is a constant, then plus integration constant C. So I'm going to take the exponential of both sides is equal to exponential minus KT plus C. Let me take the exponential of both sides. So of course you still remember that exponential negative KT plus C is to exponential negative KT dot exponential C. So we can call this particular exponential C be equal to what? A. For instance, let me call it A for instance. I can call it A naught, but I want to call it A for a reason I'll show you later. So this left hand side now resolves to A. Okay, remember exponential ln F is equal to what? F. So exponential ln A is equal to A. then you're now going to have this particular one, exponential c being a okay, I better call it a naught so that I'll not run into some confusion. So exponential c is a, then is a naught exponential minus kt. Is that okay? So I think it's more better if we take it like this. So a is equal to a naught exponential minus kt. So this is let me say general solution representing the amount at any time for an initial amount a naught. So we need to find what the value of what's k, and in order to find the value of k, we need to go back to the question and see what they want us to do from the question. Now the question says that if a is equal to a naught when t is equal to 0, prove that if the time taken for the amount of substance to become half a naught is t, then a will be equal to this one. So they're trying to tell us that if a is equal to a naught when t is equal to 0, we'll prove that if the time taken for the amount of substance to become half a naught is t, then our a is actually a naught exponential minus t ln 2 over t. So I'm going to explain this down here so that we understand. So just follow me. I need you all to trust me from here. Originally, our initial conditions have already been applied, and we have already deciphered that the value of this arbitrary constant is actually what? A naught. Okay, so this is how we actually did it. So we said a of 0 is actually a naught. Is that okay? So what you're basically doing is that anywhere you see a, you're replacing it with a naught is equal to a naught, for instance, exponential minus k of 0. So a naught is equal to a naught exponential 0, which is equal to a naught times 1, and a naught is equal to a naught. So basically, this arbitrary constant here, whatever you named this arbitrary constant here, you might have not named it a naught from the start, but I decided to name it a naught based on my experience in solving this kind of equations. Someone would have named it k, someone would have named it c, someone would have named it anything you wanted. But when you apply this initial condition, you must find out that this arbitrary constant on the right hand side must always evaluate to what? A naught, okay, on the LHS. So for our own case, our own is already a naught, and a naught is equal to a naught, so there is no need to apply the initial condition. Now they now want us to prove that if time taken for a to be half a, that's a naught over 2, if the time taken is actually t like this, then we should actually prove that a is going to be a naught exponential minus, we'll have something like ln 2 all over t, then t, something like this, I guess. So let's just confirm again so that I'm not going to jump into much problems. Okay, exponential minus t ln 2 over t. Okay, I just scattered it, it's actually correct. So we want to make that proof first of all. Okay, t ln 2 over t. So I want us to do that together. So consider a is equal to a naught exponential minus kt. Is that okay? So you're considering it. So they're trying to tell me that when a equal to, simply when a is equal to a naught over 2, well, the value of t is equal to t, like this. Are we together? When a is equal to a naught, according to this particular statement over here, when a is a naught over 2, t is equal to t. So if you replace the values accordingly in this equation, what we'll be getting is a naught over 2 is equal to a naught exponential minus k, and instead of t we're going to put t, like this. So let's see what happens. So this cancels out this, so I'm left with 1 over 2 1/2 is equal to exponential minus kt. Okay, so if we take the reciprocal of both sides, we're going to get 2 is equal to exponential kt. Okay, taking the reciprocal of both sides. So what did you observe in the left hand side? 1 over 2 became 2, and on the right hand side, exponential minus kt becomes exponential kt. So that is our application of laws of indices. Okay, when you take the reciprocal of a raised to the power of minus n, you're actually getting a raised to the power of n. Okay, so that exists and it is unique. Now if you take the take the natural logarithm of both sides, what you're going to get is natural logarithm of 2 is equal to natural logarithm of exponential kt. Is that okay? And there's a rule that states exponential or natural logarithm of exponential f is equal to f. So ln exponential kt here actually gives me kt. So invariably ln 2 is equal to kt. So if ln 2 is equal to kt, k is equal to what? Thank you very much. Ln 2 over t. So this is how we have obtained our proportionality constants. Hence, substituting it back into the equation, back into equation 2, we have our a is equal to a naught exponential minus k, where our k is then t. Okay, so if you rearrange this, you get a naught then minus t, now have ln 2 like this over t. Anyhow you want to arrange it, it's still the same thing. All of them are just related by product and division. Okay, but take note that this 2 is not directly related to t here or this t over here. This 2 is the argument of the natural logarithm, so nothing can actually multiply these 2 directly or divide these 2. The 2 is hidden in the logarithmic symbol. Okay, it's hidden in the natural logarithmic symbol. So the first case is proved. The first case is proved. So let's see what the second case 2 asked us to do. So case 2. Case 2. So case 2 says, prove also that the time taken for the amount to remain to be reduced to 1 over 20 a naught is 4.32 t. Okay, the time taken for the amount to be reduced to 1 over 20 a naught is 4.32 t. So I'm just going to memorize that. I'm going to prove it together. Case 2. Is to show Okay, we want to show that the time taken for A to be 1/20 or a 20th of A naught or a 20th of the original amount is 4.32 T. Okay, so we already know that A is equal to A naught exponential minus ln 2 over T, then T, like this. Are we together? So this is the value of what? A at any interval of time. Now we want to find the time when A is actually 1/20 of A naught. Therefore, for A being 1/20 A naught, we are going to solve for time like this: exponential minus ln 2 over T. Okay, A naught cancels out A naught. So when A naught cancels out A naught, we're now going to take the reciprocal of both sides. First of all, we have 1/20 is equal to exponential negative ln 2 then T outside over T, like this. Are we together? When you take the reciprocal of both sides, reci, okay, when you take the reciprocal of both sides, what you're going to get is, on the left hand side you get 20, and on the right hand side you get exponential ln 2 then multiplied by what? T over T. Is that okay? So I hope you still know the trick. When you take the exponential and the reciprocal of both sides, 1/20 becomes 20, and exponential minus something becomes exponential plus something. So you're now going to take the natural logarithm of both sides. So taking the natural logarithm of both sides, so natural logarithm now of both sides gives me ln 20 is equal to what? Ln, we now have exponential, what do you have? Ln 2 multiplied by what? T over T. Is that okay? And remember that exponential ln f is equal to f. So all these particular things over here is our f. So ln 20 is equal to f, which is ln 2, then you have T over T. So you just need to make small letter t the subject of the formula. Okay, make small letter t the subject of the formula. Making small letter t the subject of the formula, you're going to get small letter t is equal to ln 20 divided by ln 2 times t, like this. And if you evaluate ln 20 divided by ln 2, are we together? Our half t is actually 4.32 t. So you can evaluate ln 20 over ln 2 with your calculator and see what you get. So 4.321928 thereabout. So this is the approximate answer, and this is proved. So this brings us to the end of application of differential equations. So we've solved a lot of problems, ranging from mixing problem to motion, then we solved population, and we solved radioactivity. There are other problems, temperature problems, and a whole lot of other ones where you need to apply differential equations. Newton's law of cooling, it's just like I said, is temperature. So maybe I could develop a video on that one later in the future. Or if you have any questions on the ones I've developed so far, please feel free to ask me and leave comments. Please like, please subscribe, please share to your friends and colleagues that you know will benefit. Don't forget to hit the notification button to stay updated on our posts. So I'm going to see you in the next video, where we'll continue learning round upon knowledge on first order differential equations. We'll enter second order systems and learn how to solve them. So till then, stay safe, keep your hands hot and tight. Peace.